Hello, everyone. What we're going to do in this lecture, we're going to review some basic chemistry concepts which are behind the properties of living organisms, and particularly of biomolecules that do make up the living organisms. So what we're going to discuss, first of all, we're going to go through a review of the atomic structure of elements, and then we'll focus on those subparticles of the atoms, the electrons, that are those that are responsible ultimately for the way the elements interact with each other and for the properties of the molecule. So we'll talk about electrons, where they are found in atoms, what are the valence electrons, these electrons that are involved in sharing element connecting with each other, or atoms connecting with each other, forming molecules. And then we'll go through the chemical bonds, the type of chemical bonds, how they do arise from the behavior of electrons. Why do we talk about this? And the reason is that you see later on when we talk about different biomolecules or cellular structures, oftentimes I'll talk about polarity, hydrophobicity, hydrophilia. So different properties of these molecules which allows them to gather together. For example, like in this case, here on the left side, we have a schematic of the structure of cellulose. Cellulose is a carbohydrate made by different fibers that join together produce a very rigid, very strong cellular wall in plants. And you see that this is due to the formation of hydrogen bonds between these molecules. Why do they form these hydrogen bonds? Same thing, when we talk about cell membrane here, you see that they're formed mostly by phospholipids. So these lipids that naturally cluster together with their hydrophobic tails. And by doing that, they exclude the water on the outside of a membrane and the water on the inside of the membrane, so inside the cell. You see that there are some proteins that can actually embed in this hydrophobic environment. Some others do not. Why? What makes some of them embed in there? What makes this phospholipid cluster together, forming cell membranes? And then you see when we talk about proteins, for example, how proteins, they fold on their own, forming what we call secondary, tertiary, and eventually quaternary structures. Why? What type of bonds are involved? How do they affect the properties of the proteins? That's the reason why we talk about these basics. All of this ultimately comes back to the elements that these molecules are made of and how they share electrons with each other, or how they divide within the same molecule. The elements are distributed, the electrons are distributing within the same molecules. So everything in the universe that takes mass and occupies space is defined as matter, just using some definition here. And all matter on Earth, whether it's organic or inorganic, whether it makes up living organisms or not, is made by elements. Now, when we talk about elements, we're talking about a substance, a pure substance made by a single type of atom. Oftentimes, I will use the word atom and elements interchangeably, but there is this definition. So an element is made by billions of atoms of the same type. Basically, it's a substance made by a single type of atom, whereas an atom is a single unit that will make up the element. Now, when you look at the composition of living organisms, you see that overall, we're made by very few elements, which create an amazing complexity, but we're made by around 25 elements. In humans, you see the most abundant one being oxygen, carbon, and hydrogen, which makes up about 96% of our mass. I want you to notice one thing too, how in living organism, carbon is the second main element, but if you look, it's not the most abundant here on the Earth crust, nor in the seawater. And so we'll discuss later on why, despite its relative an abundance on Earth, carbon has become the main element in organic molecules. So there's a difference between element and atoms. When we talk about atoms, what we're talking about is the smallest units, which has the same chemical and physical properties of an element. And we'll talk about that later on, that atoms are made by subparticles like electron protons, but electrons and protons do not retain the chemical and physical properties of the element they come from. So the atoms is that smallest unit. The name itself, atomos, comes actually from the Greek atomos, and was proposed by this Greek philosopher more than 2,000 years ago, 2,400 years ago, actually, and which used this word to explain his philosophical, and I stress philosophical, not scientific concept, where he was saying basically that if you take anything on Earth, it was just philosophizing this. You take anything on Earth and you start chopping it, like an apple, for example. You start chopping it, keep chopping, keep chopping, keep chopping. At a certain point, you would hit a point where you hit something in there, you had no idea what it was, that could not be cut anymore. And in Greek, that you cannot cut, you say atomos. That's where the name comes from. And then was later on reused by scientists to explain these units of all molecules and elements. Now, when it comes to atoms, they're always represented by one letter. For example, hydrogen here is represented with H, which is the first letter of hydrogen, or two letters. Now, these two letters can correspond to the first two letters of the name, like helium, He, or sometimes they might not correspond to the one commonly used in English, but they come from the name in either Latin, the original name, like sodium, the Latin name is natrium, so Na, or in German sometimes. It depends on the language in which this element was discovered and described originally. Now, all elements and atoms have their own unique properties, okay? And these have been summarized since the second half of the 1800s in a table called the periodic table of elements. It is not the purpose of this lecture to discuss this. I'll leave it up to proper chemists to talk about that. I'm a biologist. I just use this as a tool. But all I want to show you is that all the properties we'll talk about later on can actually be found in these tables. Table where all elements known, whether they're natural or are man-made, have been put together here based on different properties, based on their chemical properties, reactive properties, and electron distributed. They're organized in columns or rows that basically follow so the increase in atomic number. So this table later on will allow you to find the information like the atomic number, which is described here on the top left of the element. There is the name of the elements, and then there is the atomic mass, plus other information like the electron distributions in the different shells, different energy levels of the elements. Now, atoms, they're all made by three main subparticles. Okay, two of them are found in the nucleus, and they're called the protons and the neutrons. They are particles with a certain mass, but they are different. Protons, they actually do carry a positive charge, whereas neutrons, as the name says, they are neutral. They don't carry any mass. Oftentimes there is the same number, but there might be different numbers of protons and neutrons in the nucleus. Together with that, there is a third subparticle called the electrons, which are not found in the nucleus, but somewhere, not in orbits like is described here, but somewhere around the nucleus. Okay, they can move around there. Nobody really knows where they are. You can just guess where they are when we talk about orbitals. Now, every element, so every atom and every element has its own ID, as you have your ID when you go around, which is referred to as the atomic number. The atomic number is this number you find on the top in the periodic table, like 5 in this case for boron, or 8 for oxygen, or 6 for carbons here, which basically tells you how many protons are present there. One element will always have the same type of protons. So now it means that if I tell you, okay, the element that has 8 protons, you automatically know I'm talking about oxygen. That's its ID. There is only one element, oxygen, that has 8 protons in the nucleus. If I tell you 6, you know it's carbon. And so I tell you 1, I'm talking about hydrogen. The number of protons is referred to as the atomic number. Now, there's another value that you find in the periodic table, which is the atomic mass. Atomic mass is different than the atomic number. And what it corresponds to is actually the mass of an element, which is represented by the total mass of the two main subparticles that make it up, so protons and neutrons. Electrons are not accounted for. The reason being that the mass of an electron is so small that is basically, you can actually ignore it. But this number that you see here correspond to the mass of the protons and the neutrons combined together. Now, by definition, this is measured in atomic mass unit, or AMUs, where you have that one atomic mass unit correspond to the mass of one proton and a mass of one neutron. So if you see a mass, atomic mass equal to 12, and you know it's carbon, then it means that there are 6 protons and 6 neutrons. So the atomic mass allows you to actually figure out the number of neutrons if you already know the type of element you're talking about. Now, the number of protons, as we say before, which is the atomic number, is always the same. That's the idea of an element. However, the number of neutrons for the same element can differ. You can see here some example here. So, for example, for hydrogen, you always have one proton, but you may have different forms of hydrogen, which, by the way, are treated exactly as the same element in biological molecules. So meaning that in your DNA, you can find this hydrogen or this hydrogen or this hydrogen as if they were exactly the same hydrogen. So they all have one proton, but they have different number of neutrons. So this second form, referred to as deuterium, has one neutrons, whereas the third form here has 2 neutrons. Therefore, the atomic number will always be the same, it's 1 here, but the atomic mass, or the mass number, will be different. In this case, will be equal to 1 atomic mass unit. In this case, 2 atomic mass unit. In this case, 3 atomic mass unit. Now, these different forms are referred to as isotopes of hydrogen in this case. Carbon and other elements follow the same thing. These are the 3 main isotopes of carbons. You have carbon-12, carbon-13, and carbon-14. These numbers here on the top left correspond to the atomic mass of the different isotopes. Since we know that carbon always has 6 protons, now this allows us to figure out the number of neutrons. So in this form here, you have 6 protons and 6 neutrons, therefore carbon-12. In this case, you have 6 protons, but 7 neutrons, and therefore carbon-13, and so on. So with different atomic mass. Now, some of these isotopes are actually very helpful in science. And the reason is that some of these isotopes are very stable. For example, when it comes to carbon, carbon-12 and carbon-13 are very stable. Okay, they stay there pretty much forever in that form. Whereas carbon-14 has a tendency over time to decay, to convert into something else, lose neutrons, protons, and so on. When they do that, these isotopes, they actually emit radiations, and therefore are called radioisotopes. Now, this decay occurs always at the same speed overall. And there is a volume, a parameter called the half-life, which tells you exactly how fast this happens in a specific isotope. So, for example, for carbon-14, the half-life, which corresponds to the time that it takes for 1 mass of that specific isotope to become half. So if you start from 1 gram of carbon-14, how long will it take to go to half a gram? So it'll take you 5,730 years. That's the half-life of carbon-14. So carbon-14 is relatively stable, but still over time, it will decay. It will emit some beta radiations, certain type of radiation, and it will convert into something else. And by doing that, its mass over time will get less and less. When it gets half, you have 1 half-life past, so 5,700 years. When it gets half of a half, or whatever was left, so 1/4, then you would have 2 half-lives passed. When it becomes half of what was left, so 1/8, you would have had 3 half-lives. So here you are at 17,000 years, just to give an idea, 1790, 190, and so on. These curves shows you the relationship between the original mass and the time has passed in half-lives for any element. So after 1/2, you would have half left, 2 half-lives, 1/4, and so on. Now, as I said before, radioisotope, they decay, and when they decay, it takes them a certain time to become their half-life, and they emit radiations. Both properties, the time that it takes, so the half-life of an element, and the type of radiation that they emit, can be used in science for different purposes. First example can be used to determine the age of a certain living sample or former living sample that's been found. Carbon-14 is used for that when you want to have a big picture. Obviously, this work in terms of dating, looking far away in time. So how does it work? Well, as I said before, the three main forms of carbons found in living organisms are carbon-12, carbon-13, and carbon-14. Now, when you are alive, the relative amount of these three carbons in your organic molecules, in your bones, in your liver, wherever, is constant, always stays the same. You have about 98.9% of carbon-12, 1.1% of carbon-13, and 0.0001% of carbon-14. So 1 to 10 to the minus 8, to 10, sorry, carbon-14. That's the relative percentage. If you put it together, it comes a little bit more than 100 because I rounded these numbers up. Now, what happens is that so if you keep eating, you keep this ratio constant. But once you die, last time I checked, we stop eating. So if you stop eating, then at this point, what you have is that this picture, which is there in your carbon, in your body when you're dying, with time, it will change. Why? These two forms are stable. Carbon-12, carbon-13 are stable, whereas carbon-14 over time will decay. We know the half-life. Start decaying, becoming half, so this number will become half after 5,330 years, and so on. So you can actually use this information. So if you determine the percentage of carbon-14 found in any sample, certain point, and compared to the one it should have been if the sample was fresh, basically, you can figure out how old that sample is. One example. Imagine you're doing work in your basement and you're breaking the concrete. Oh my gosh, you find a huge bone, a 100 kilograms bone. Cannot be human. I don't think there is any animal nowadays that could have a bone that big. Maybe some big waves, whales, and so on. But looks very old. You want to figure out how old it is. Now you know that if it was recent, right, this would be the number you would have to get there in terms of carbon-12, carbon-13, converting from percentage to grams. I use 100 kilograms, so kilograms, sorry, this will be kilograms, not grams, my apologies. And carbon-14 here. This is all kilograms, please add a K to all of them. But now, you break this down a little sample and you get it tested in a lab and you find out that the actually amount are 98.9 grams, so the same for carbon-12 and 13. They're stable, you expect to get that. But the carbon-12 is not what you would expect it to be, so 1/10 to the minus 8 kilograms, but 0.125 10 to the minus 8 kilograms. So if you now calculate the ratio between these two numbers, you see that what you get there conveniently, in my calculation, corresponds to 1/8. The carbon-14 you have is 1/8 of what you should have had if it was a fresh sample. So what it means is that, practically speaking, is that 3 half-lives might have passed for the sample to go from this mass to this mass. Since you know how long each half-life of carbon-14 is 5,730 years, now you know that 3 half-lives have passed, you can actually guess that this gigantic bone in your basement is about 17,190 years old. Second example, how the property of radioisotope can be used is by actually using the radiation emitted. And one example is how iodine, a certain type of iodine isotope called iodine 131, is used to treat thyroid cancer. The thyroid is an organ that you have located basically at the bottom of your neck. It's an extremely important gland. We'll talk about that in BIO359. It's a gland that basically controls most of your metabolism, plus the function of other organs as well. Extremely important. However, sometimes some of the cells may become cancerous there, and so they have to be removed. How do you remove it? Usually it's removed by surgery, but you might have a chance that some of these cells may have spread throughout your body. In order to treat cancer, so the cell particularly that have spread around the body, what different doctors use is the property of thyroid cells, even normal cells, which is the one to uptake iodine. Thyroid cells, with a few other cells, particularly in the adrenal gland, can actually actively pick up iodine. Why do they do that? Because they produce a hormone called the thyroid hormone, which actually includes iodine, its structure. So protein has iodine attached to it. So they do that normally. Even the cancer cells, once they spread around, they still retain the same property of picking up iodine. So now, if you can use a form of iodine that simulates, basically is identical to the normal one, but the difference it has is that it actually emits radiation that can actually kill. So these are high energy radiation that are emitted by this radioisotope, and they can penetrate up to 2 millimeters in size. Now you have that. If you give a patient, imagine this being a patient, okay? This is actually the picture of a body. It's called a scintillography, where you measure the distribution of radioactivity in the body of a patient that has been given iodine 131 orally. So you can see the dark spots tell you where most of the radioactivity is. And you can see this is the head. Most of it is actually where the thyroid is supposed to be. And then another big chunk is in the stomach, which makes sense. The pill was given orally. So with time, this will go down because there will be some body secretion from this patient. The urine will remove it as well from the circulation. But whatever is in the thyroid gland will stay there, okay, for some time. Now, the half-life of iodine 131 is 8 days. It's now measured in years. So after a few days, this radioactivity will keep going down. After 8 days, we should be half. After another 8 days, 16 days, will be 1/4, and so on. So it will decay fairly quickly. Still, this patient will need some isolation for some time. As you can see, so iodine 131 is picked up by the thyroid cells. If this patient had metastasis, let's say in the lungs, you start seeing dark spots here as well, because these thyroid cells here will still be picking up iodine 131. And when this happens, now you have that these cells have this radioactive isotope of iodine, and this radioactive isotope is producing high energy radiation, which can spread up to 2 millimeters. This radiation can actually break the DNA in the cells that pick this radioactive isotope up, and also some neighbor cells. By doing that, you can create extreme damage to the tissue that has picked up the radioactive isotope and therefore kill the cells there. So even if they're spread throughout the body. Moving on here, we talked about proteins, neutrons, the atomic number, atomic mass, isotope. Now let's move to the third subparticle, which is the star, if you want, when it comes to the properties of elements and molecules, which are electrons. These are very subatomic particles. They have a mass which is about 20,000 times smaller than protons and neutrons. So this is the atomic mass unit value. That's the reason why they're ignored when it comes to calculate the atomic mass of an element. Now, the number of electrons in a neutral atom or element always be equal to the number of protons. So usually, so what it means is that an element will be neutral to start with. They are located in areas called orbitals, you see in the next slide, and they can be shared between different elements. These are those subparticle molecules, again, which creates the bonds give the property to the behavior to the different elements, you see also when it comes to BIO359, when we talk about cellular respiration and we'll talk about photosynthesis, these are actually the molecules that are used to actually move the energy around, to store it around. They have a lot of energy, these electrons. So where they are located outside of the nucleus and in areas of probability. Nobody really knows where they are, but you can guess where they could be based on their energy level. And these area of probability are called orbitals. So there are different level of different type of orbitals, which are named as S, P, when they look like this, cute, almost like an 8, but it's a three-dimensional one, D, F, and so on. You can move on to different types of orbitals there. It's not the point of this lecture to discuss orbitals. However, how these electrons end up in these orbitals. First of all, each orbitals can hold up to 2 electrons. Now, all electrons would tend to go to a lowest level of energy. So what it means is that if one element like hydrogen has only one proton and therefore one electron, this electron will be found in an orbital, the orbital that has the lowest level of energy in hydrogen. So it will be found. This picture here shows you the level of energy of the different orbitals. Now, the lowest level of energy here, would have only one s orbital. So it could only host up to 2 electrons here. So when it comes to hydrogen, the only electron that is there, it will be in this type of s orbital there. Then, when you start having more than 2 electrons, they will move to a second, higher level of energy because the lowest level of energy will be filled. So first, we'll move to a second type of s orbital, which will be named as 2s in this case. Once you have more than 4 electrons in total, then the next one will move to orbitals for each level of energy here, 5d, and so on. And so they keep filling up in the direction shown by this picture right here. In reality, these apply some elements, not to all of them, even though in chemistry they'll teach you that this applies to all elements, but they keep going up. So if you know the number of electrons of any element, then you start filling them up. So for example, calcium has 20. The first 2 will be at the lowest level of energy here in this orbital. The next 2 will start first going to these s, 2 of them. Now there are 3 p's at this level, so another 6 will go here. You're already at 10. The next 2 will go to the next, the 3s, and then another 6 here. So you're going to get at 18. Now, instead of going to the d level, the next 2 will actually go to the 4s orbital there. But that's how they will be distributing. Now, representation of the location of electrons oftentimes is done use what is called a shell model. The shell model basically depicts the energy level of the electrons. Instead of telling you exactly in which orbitals they are, it tells you at what energy level they are. And they're represented as concentric circle, basically, or shells, which have an increasing amount of energy the farther they go from the nucleus, which will be right here represented by this dot. So this is the first energy level, first shell, which will correspond to a single s orbital. Because of that, one s orbital can host up to 2 electrons. On the first level of energy, you can only have 2 electrons. When you move to the second level here, you start having one s, which can host 2 electrons, and 3 p's. So you can have 8 in total. So the second level of energy could have 8 electrons. When it comes to the third level of energy, keep in mind that this works up to certain type of elements, basically up to calcium, based on their behavior, since the next electron, calcium, will end up in the 4s. So the third one would have 8 maximum as well, and so on. So when it comes to create a shell model, you always start from the lowest level of energy. So for example, if you're drawing hydrogen and you're just representing, obviously the electrons, the protons and the neutrons are ignoring this model. So hydrogen has one proton, therefore one electron. You would just put the first electron in the lowest level of energy. When it comes to helium, it has two protons and therefore two electrons, and you put both of them in the first level of energy. When it comes to elements that have more than two electrons, at this point, the next electrons will be first placed on the second level, so the second shell, until you reach 8 of them. Again, we're following basically this distribution. It can get up to 8. And then the next level will be moving to the third orbital here. Again, this works up to calcium. After that, there's going to be, so the third can actually host up to more electrons than 8 because you start having the d orbitals and so on. Now, it has been shown, again, that elements, so when you start feeling this and you look at the property of elements, we know, for example, that neon and argon, what they're called noble gases, they're non-reactive type of elements. And what has been noticed is that they are non-reactive and they have 8, always end up having, if you look at the outermost shell, is the one that includes the electrons that we call the valence electrons. The valence electrons are the outermost electrons. These are the electrons that are the more reactive one, the one that are easier to lose or share overall. And now it's been noticed that non-reactive elements like neon and argon here, they have 8 electrons in their outer shell, so 8 valence electrons. And so this has been translated in what is called the octet rule, that basically states that an element will become inactive, stable, if it can reach 8 electrons in the outermost shell, so 8 valence electrons. Some elements don't have them, but basically they will become stable if they can reach that number. Okay, and this is the base to explain how do elements interact with each other or how they behave. Ultimately, they are behaving to achieve this stability through achieving 8 valence electrons altogether. How do they do that? Well, some elements, they do that by losing or acquiring additional electrons. Only electrons can move out except for radioactive decay, but forget about that. But only electrons can basically move from an element in or out. And by doing that, so if you consider an element to start with would have an equal amount of electrons and protons, so it will be uncharged. But some elements, they actually do lose or acquire electrons. And by doing that, they acquire a charge. In that case, they're referred to as ions. They become ions. Now, if an atom loses one or more electrons, sodium loses one, calcium, magnesium, they lose two, for example, they would acquire, since they have less electrons now than protons, they would acquire a positive charge, and they're referred as cations. If an atom instead gains one or more electrons, like chlorine, that becomes chloride, acquires one electrons, would have at that point more electrons than protons and would acquire a negative charge and is referred to as an anion. Here are some examples. Sodium, here on the left, on the top left, and chlorine here on the top right. So this is their normal configuration where they are neutral. Okay, so if you take pure sodium, that's how it will look. Sodium has 11 protons and therefore 11 electrons to start with 2 of them at the lowest level of energy, so the first shell, 8 of them at the second level of energy. This together brings to 10, and the last one is on the third level of energy, on the third shell. So it has only one valence electrons. Okay, do you remember valence electrons are those in the outermost shell, so the highest level of energy. Chlorine instead has 7 of them on the outermost shell. So it has 17 protons, therefore 17 electrons, 2 on the first shell, 8 on the second, and 7 on the third shell there. So both of them do not fulfill the octet rule. Sodium would need 7 extra electrons here to fulfill it. Here chlorine would need only one. So how do they actually somehow fulfill the octet rule is in opposite way. Now, sodium, because also of its electronegativity, and we'll talk about that later on, does not really hold its electrons very tightly. And for this reason, tend to lose this extra electron that it has on the higher level of energy. By doing that, now has two things. It ends up having more protons, one more protons than one electrons, therefore becomes a cation with a positive charge. Not only that, but at this point, it ends up having also the outermost shell completely filled with 8 electrons, right? And therefore, it acquires stability. Opposite to that, chlorine tends to, because of high electronegativity, again, we'll talk about that later on, tends to gain electrons, to pull electrons very tightly. By doing that, can grab electrons that are actually around from other elements. So we tend to acquire an electron. By doing that, two things again. It ends up having one more electron than the number of protons it has, and therefore acquires one single net charge, which makes it an anion. Sorry, this will be anion. Please, let me change it here. So everyone is clear with that. There's a mistake. Anion. So this will be anion, not cation. Okay. A-N. Okay. A-N-I-O-N. When this happens, now what happens there is you have two elements with opposite charge that tend to interact with each other. Later on, you see this is the base of the formation of what is called an ionic bond. Now, in general, and we can stop here. Actually, I'm going to divide the video here. So I'm going to stop here. In the next video, still part of the same lecture, we'll talk about the basics of chemical bonds.